we kind of talked about this a little bit already, but this is our first formal time that we're talking about this, is dealing with percent dissociation. And what I want you to recognize is that when you look at percent dissociation, okay, it's actually equal to the hydrogen concentration, and this is at equilibrium. Now you don't really have to put the EQ on there, but it kind of gives you an idea. Divided by whatever your acid was, your concentration of your acid initially, okay? So whatever your hydrogen concentration is at equilibrium divided by what you started with, of course, times 100. Okay. So if I'm looking at, say, a strong acid, and let's say that I start off with a 1 molar HCl, okay? And this really helps to seal that. That if I start off with 1 molar, what will my concentration of hydrogen be at equilibrium? 1 molar. What was my initial concentration? 1 molar. So 1 divided by 1 times 100 is 100% dissociation. Okay, so with the strongs, whatever we start with better be what we finish with. And with the weak, obviously this value should be greater than this. So that's what percent dissociation is. You can probably see that in the homework. Same thing with the bases. If you have your hydroxide concentration, okay, and then whatever your B was at the beginning, okay, so your hydroxide concentration at equilibrium and whatever your base was initially. So if you have a strong base, and same thing if it's a 1 molar, these numbers will be the same, so it'll be 100% dissociation. Okay. Common ion effect, that's the major topic for today. Common ion effect is actually something that's pretty important because it's a nice segue into buffers, which we won't talk about until well after Thanksgiving. But common ion effect means that we have a system at equilibrium and then we're going to add a salt to it to see how it changes your pH. So common ion effect deals with, we've got either a weak acid or a weak base that's already at equilibrium, and then we add a salt that has a common ion, and it's going to cause the pH to change. Now I can talk on for many, many hours on what common ion effect is, but I think it really helps when you see it. So this first sheet actually has an example problem on the bottom here, and it's worked out on the back. So I'm not going to talk about that one, but that's a worked out problem for you. So let's go to the example sheet. Part 2, and I'll talk about common ion effect as we work through this. Probably a little bit better way of doing it. So examples part 2, it has the equation. Let me write it up here. So that's not one of our polyatomics, so C3H4O2, and it dissociates into this. Okay. Acrylic acid, this is acrylic acid, is a monoprotic acid that dissociates in an aqueous solution as represented in the equation above. Acrylic acid is 0.6433% dissociated in 1.35 molar solution of the acrylic acid. And this is a past AP exam question, that's why it's worded this way. It says for parts A through C, below assume that the temperature remains at 298, which we do nothing with the temperature, but they always have to put that in there. Alright, so part A says write the expression for the acid dissociation constant, the Ka for this, and calculate its value. Okay. So the first thing that we want to do is write the Ka. So how would I write this? Good, so I'm going to put the products over the reactants and do show the charges. So the hydrogen plus, or times the acrylate over the acrylic acid. Okay. And do we need to make an ice chart for this?
What?
Do we need to make an ice chart for this? No. If you want to, it's not wrong, but we really don't need to because the problem says that the acrylic acid is 0.6433 or 0.6433% dissociated in a 1.35 molar solution. So really, what we've got is a 1.35 molar solution that we started with, We don't know exactly what our hydrogen concentration is, but we do know that we have this, okay, as our percent dissociated. And that's a percent, so that's not really 64%, all right? So how in the world can we find out what the hydrogen concentration is? Yeah, so we're going to do 1.35, we're actually going to bring it right up here. So the hydrogen concentration is equal to 1.35 times, and this is percent, so how do I really write that value? Yeah, put 2 zeros in there. Okay. So you have to recognize that that's a percent. That's not 64%, that's actually less than 1%. So whatever that equals, 8.65? 85 times 10 to the what? All right. So there is our hydrogen concentration. Is it also our acrylic concentration? Yeah, if you were doing an ice chart. So let's do the lovely arrows here. So we have our 8.65, and did anybody else get that value? Okay. Not that I don't trust you, Wes. Times 10 to the negative 3, square that. And since we know what x is, we're going to do 1.35 minus that. And that'll be our Ka, whatever that is. So 5.6, and again, I'm sure I'm rounding this, times 10 to the negative 5. Anybody get that? Okay, so that's our Ka value. So we might want to put that somewhere. Actually, I'm going to erase that here. So I'm going to put my Ka over here. So 5.65 or 62 times 10 to the negative 5. Okay. All right, so that's part A. Part B says calculate the pH of this 1.35 molar solution. So what are we going to do? Negative log of what? Hydrogen, which is this?
No.
Absolutely not. And that's what you want to be careful of, because this is the last thing that you have in your calculator. And this is one reason why College Board does this, is to make sure that you recognize, ooh, just because that's the last thing in my calculator, that's not what I'm taking the negative log of. You want to take the negative log of the hydrogen concentration. So pH is the negative log of your hydrogen concentration. That's one reason, and you guys might get tired of seeing me write that, but I'm always going to write that, because by doing that, that makes me stop for just a moment and say, wait a minute, that's the Ka. I really want that value. And if I can get you to stop for just a moment, it's probably going to save you quite a few points. So whatever that is. Yeah, just because it's the last thing in your calculator, don't be happy with that. It's like 2.06?
Yeah.
Okay. All right, so I'm going to put that over here. So pH is equal to 2.06. Okay. All right. Let me clean the board off here. So everybody good with this? Really, so far the only new thing is this percent dissociation. And if you needed to make an ice chart, again, there's nothing wrong with that. Just realize that if you have percent dissociation, that you may not need to make an ice chart. But some of you are creatures of habit, and there's nothing wrong with that. Part C. Calculate the pH of a solution formed by dissolving 1.35 moles of solid potassium acrylate, the KC2H4O2, in 2,550 milliliters of a 1.35 molar solution of the acrylic acid. So what we're doing is we have our solution at equilibrium, and now we're dropping some salt into it. And it wants to, and it says, assume that the volume change is negligible there, or doesn't change. So here's what we've got. we've got our solution, our 1 point, does it say how much? It doesn't, or does it? Yeah, we have our solution that has a volume of 2,550 milliliters, and it's our 1.35 molar solution of our acrylic acid. Okay, and it's at equilibrium, which means it has a pH of 2.06. So those are our standard, or our conditions at the moment. Now what we're going to do is we're going to drop a salt into there. Okay. Splash. Okay. And it says that we have 1.35 moles of this, and this salt actually is potassium acrylate. Okay. So, and then the question wants to know, after we drop it in there, what will the new pH be? Okay. So before it's 2.06, after we drop it in there and allow it to dissociate, we want to find out what our new pH is. And assuming that we have a really neat system, the volume won't change. So here's what we need to do. So we need to start off with our salt, which is, okay, and what do I do with that? Do I leave it as is? The answer is no. Very good. So we're going to dissociate it. This is just like what we did the last time that we met. Okay. So here's our salt. And what is the potassium going to do for this? Nothing. It's just going to be a spectator. Now again, do realize that there will be potassium ions in this, except it's not going to do anything. It's not going to cause the pH to go up or go down, because that's a conjugate of a strong base. However, the C3H4 is a conjugate of what? Of the acrylic acid. And we have a Ka value for our acrylic acid, and we actually have the equation. So if this is a conjugate of an acid, this behaves as a what? A base. Very good. So I'm going to put water there. I need a new marker. And what's going to be on the other side of this equation? The acrylic acid. Good. So the H. So again, we're going to have that back in there. And what else? OH. Very good. Now, here's the deal. Since this is a continuation of a previous problem, do we know our concentration for our acrylic acid? Yeah. Actually, it's 1.35. Okay. Because how do we know that? It says that it's 1.35. We don't care about that. Do we know our concentration for our acrylate? Not yet. We have a 1.35 moles. So to find the molarity for this, and a lot of you had problems with this on the quiz. How do you find molarity? Moles over liters, or moles over volume. A lot of you were given the volume and you multiplied it times the moles. I don't know what that is. So 1.35 moles over this in liters, which is 2.55, and that'll equal something. So 1.35 divided by 2.55. So 0.529, anybody get that? So there's my concentration for my acrylic. So here's something that's pretty cool. Oh, and the hydroxide. How much hydroxide do we have here? This is a trick. Don't say 0. Good. We have approximately 0. It's a value so small that we don't want to write it down. Okay. However, do realize that our system is at equilibrium here from the previous step. So from earlier on in part A and B, we do have a concentration for the hydroxide because we have a concentration for the hydrogen. However, it's so small that we don't want to say it's 0. Okay? But don't get your panties in a bunch that it's approximately 0, because we get to use the 5% rule. All right? Now, is this at equilibrium? Don't know. Okay? And that's the beauty of the 5% rule, because I could say that I added this to the solution, and if I add this, which direction does it shift? away from the addition. So we could subtract x, that's going to be a dash. Okay? And then 0.29 minus x, dash, and then 1.35 plus x. Now, here's what you don't want to do. Don't write x. What we're really looking for here is the OH concentration. Okay? Don't write x, because some people are going to go, well, if you add, it just gets really bizarre. So just write what we're looking for. Okay? Now, when we write our expression for this problem, we're going to have the products over the reactants. So this is our Kb, right? Because we have hydroxide. So we'll have HC3H4O2 and OH over our acrylic. And that's our Kb. So then we can plug in our values for these. So we have 1.35 plus x times the hydroxide concentration over the 0.529 minus x. Did you guys say you wanted to use 5%?
Yeah.
Good call. Okay. So now we've got 1.35 times the hydroxide, because we can drop whatever is added to or subtracted from a given concentration. And do we know the Kb? We don't know the Kb yet, do we? So how in the world can we find out what the Kb is? Because we have to have a Kb value, because we have a Kb and hydroxide. So what do? Yeah, we're going to find Kb by doing Kb is equal to Kw over Ka, and we need to do that. So 1.0 times 10 negative 14 over my 5.62 times 10 negative 5. That equals something. So we'll say 78 times 10 to the negative 10. Anybody else get that? That's our Kb, right? So that's our Kb. So now that we have our Kb value, okay, plug that in. Negative 10, bring that up, bring that down, because we're looking for hydroxide, right? So the OH is going to be equal to 1.78 times 10 to the negative 10 times 0.529 divided by 1.35. And whatever that equals, so 6.97 times 10 to the negative 11. Okay. Now what do? What's the question want? pH. It wants this. So can we find pH? Yeah, we can find pH. If you want to find the POH, that's fine. I'm going to go ahead and just go right after it. Okay, so I'm going to do the 14 minus, because again, that's the POH. Uh, 6.97. So 3.84. Anybody get that? All right, now here's what I want you to think. I want you to think about this. Does this make sense? Okay. Because we always have to have some logic behind our answer, which is always good. If, before I placed the salt in here, we had a pH of 2.06, right? And I placed the salt in this solution, this acidic solution, and how did this salt behave? Like an acid or a base? A base. So when it started to dissociate and it actually started forming hydroxide, would we expect the pH to go up or down if we added more hydroxide to the solution? should go up. So it went from 2.06 to 3.84. That's a good result. We want something like that to take place. Okay, so as a real quick check, you can look at your pH before and then compare it to your pH after and say, okay, good. We added a salt that behaves like a base, which forms hydroxide, so it should cause the pH to be elevated. Or, another way, reduce the amount of hydrogen concentration. Cool. Doesn't this look like fun? That was a past AP exam question. Calculate the pH of a 1 liter, 2.22 molar nitrous acid solution at equilibrium. Then calculate the pH of a solution when 15.3 grams of solid lithium nitrite is added to the solution at equilibrium. Assume that the volume change is negligible. The Ka value for HNO2 is 4.0 times 10 to the negative 4. That's nice. Okay, so we want to first of all calculate the pH of our HNO2. Okay, is that a strong or a weak acid? Strong? It has a Ka value of 4.0 times 10 to the negative 4. Is that a strong or a weak acid? It's very weak, very good. I don't give you Ka values if it's strong. So this dissociates by forming hydrogen and nitrite. Okay? It says that we have a 2.22 molar solution of this. So how much hydrogen and nitrite do we initially have? How much hydrogen and nitrite do we initially have? Zero. We're not given any information about that. So this is just like the good old days. Remember the good old days? Oh, they were lovely. All right, so we write the expression.
5% rule.
Easy, girl. I don't know, can we use the 5% rule on this? Yeah.
So you're going to speed of lightning.
What's that?
You're going to speed of lightning.
Oh, I thought you guys knew what to do there.
Nope. Speed of lightning.
All right, so yeah, I should have been able to do that in my head. Okay, so there's my x squared. So x is 2.98. And what does x represent here that we care about? H plus concentration. So we can find the pH first. That's what the first part of the question was asking. So 1.53. Alright, so there's the first part of the question. And then it says, okay, so calculate the pH at equilibrium. We did that. Then calculate the pH of a solution when 15.3 grams of solid lithium nitrite is added. Okay. Alright, so lithium nitrite.
Okay, you don't care, but you sit there and get every single corner of it and you clear it off.
It's my board.
Yeah.
Alright, so how's this dissociate? Is this a single arrow or a double arrow? Single, good, it's the salt. So the lithium dissociates, and then we have the NO2 negative 1. So, what's?
Lithium doesn't.
Good, lithium out of there. So we're going to do our ice chart with the nitrate. And it's a conjugate of a what?
Acid.
An acid, HNO2, good. So this will behave as a base. We're going to rip the hydrogen off of there. And you'll have HNO2 plus hydroxide. Isn't this easy? Just so tedious. Alright, and then it's, oh, look at what I threw at you. 15.3 grams. What do you get to do with that? Can we do this all in like one step? Do we know our volume for this solution? No? Yeah? 1 liter? Okay, so I'm going to put my grams over my volume, and then I'm going to convert my grams into what? Moles. Okay. Somebody barking over there? Alright. Let's get the molar mass for this. So lithium is 6.94 plus 14.01 plus 2 times 16. So 52.95 grams. So my molarity, because again, the grams are going to cancel out. We're going to have moles over liters. So point, is that 289? Anybody get that? Alright, so there we go. We have our 0.289. Our water, obviously dashed. Now again, what we're doing is we're placing this salt in our nitrous acid solution. And how much did we have? I lost my question. There it is. 2.22. And the hydroxide is what again? It's approximately 0, because this is the second part of the question. I did what with the bottom? Oh, okay. And so again, minus x plus x. And then we're going to be looking for the hydroxide concentration. Okay. So we need to write our Kb. So products over reactants, HNO2. NO2. So we have 2.22 plus X times the hydroxide. Oops, that should be minus X there. 289 minus X. Taylor, did you want to use 5%?
Yeah, I can't focus.
You can't focus? Oh. I'm sorry, my bad. Let's make that a better arrow. Alright. And that was equal to, we didn't find our Kb yet, did we? Beautiful. What was our Ka? 4.0 times 10 negative 4. So Kb so 2.5 times 10 negative 11. So let's start swinging these babies across. So your hydroxide is equal to Is everybody having fun today? How could you not? It's hump day and it's kind of warm outside. So now what do we do? Can we find pH from that information? Heck yeah. So we'll do 14 minus the negative log. I can't believe you guys didn't want to try this one on your own. Don't you feel bad about it now? I know. What's overwhelming?
The regret.
The regret. Oh yeah. I can understand that. All right, so 2.51. Anybody get that? All right. Now, again, I need to ask you: does this make sense? I have my original solution of the nitrite or nitrous acid at 1.53. I go and add a salt that acts like a base. So should the pH go up? Yes. Okay. It went up. Isn't that cool?
So if it was an acid, it would have went down?
Yeah, but we won't add an acid to an acid. But I could add an acid to a base.